Hey everyone, so today we're starting a new chapter which is thermochemistry. Thermochemistry is chemistry that involves the transfer of heat. So it could be a chemical reaction where heat is released, like a combustion reaction, or it could be a reaction where heat is absorbed and it makes things colder, so things like refrigerants and stuff like that. So thermochemistry, we're going to talk about this, and the main thing with thermochemistry is that it involves energy, right? Well, what is energy? Energy is the ability to do work on an object. So, if we break a bond, a little bit of energy could possibly be released, okay? If we have a lot of bonds and we break them all at once, then a bunch of energy could be released. This could be helpful in terms of heating an area, right? If we're releasing a bunch of energy from these bonds breaking, we could heat up an area, or we could use it to possibly move things, right? Like in your battery, if we have a chemical reaction there, that could produce enough energy to actually power something. So that's what we're going to be talking a lot in this chapter. And the two types of energy that we're going to focus on first are potential energy and kinetic energy. And you've probably learned about these before. Potential energy is just energy based on position. So specifically, how high off the ground you are, okay? The higher up off the ground you are, the more potential energy you have, right? Like if you're at the top of a roller coaster, you're going to have a lot more potential energy. Kinetic energy is the energy of motion, specifically how fast you're moving. The faster you're moving, the more kinetic energy you are going to have. So let's dive into potential and kinetic energy a little bit more, where we do some calculations. So let's start with potential energy first. Potential energy is represented by the equation potential energy equals mgh. Okay, well, what does mgh mean? Well, first of all, potential energy is what PE stands for, and it is measured in joules. Okay, it's measured in joules. 1 calorie equals 4.184 joules. We'll talk more about that later. So I'm going to go ahead and put this in brackets to simplify our units. M is mass. And the important thing you got to know here is that mass is, let me put potential energy equals, mass equals, or M equals mass. Mass is measured in kilograms, okay, not grams, kilograms. So whenever we're dealing with these energy equations, just know that your mass is in kilograms. And then H, right, I said potential energy is due to your position. Well, it stands for height, okay, which is measured in meters, right? I got a meter stick here. All right, that's what the units are measured in. And then G, what does G stand for? That is a constant, and it is the acceleration due to gravity. Okay, if you're on Earth, your acceleration due to gravity is going to be 9.81 meters per second squared. So G is always going to be 9.81. It's like C equaling 3 times 10 to the 8th, or it's like in Pivnert, R equals 0.08206. G just equals 9.81. So that's the equation that we're dealing with, right? So let's go ahead and let's do an example. Let's say that we got a building here, right? There's somebody sitting on top of the building with a bowling ball. And let's say that this building is 35 meters tall. Okay? It is 35 meters tall. Actually, let's go 30 meters. Because that's what it says in my book. 30 meters tall. And let's say that this bowling ball is 5 kilograms in weight. Okay? And then let's just draw something down here for it to smash, like a watermelon. It's pretty good drawing of a watermelon. Okay? And all I'm going to ask you is, what is the potential energy right? So I'm asking, what is the potential energy of the bowling ball? Well, remember, potential energy deals with height, which is all about mgh. Big thing here, make sure that your mass is in kilograms, which it is, and that your height is in meters, which it is. So mass is 5 kilograms, so we'll put a 5 in there for mass. Remember that G is 9.81. And remember that height is 30. So pretty simple calculation here. We just plug and chug, and we get something like 1,470 joules, right? Joules. Unit for energy. They're 1 calorie, they're 4.184 joules in a calorie. Let's do another example real quick. Say you're pretty radical and you skateboard, okay? You go off of this ramp and you're sailing. You don't know where you're gonna land, but you're skateboarding, you're sailing. We know that you and the skateboard, we'll say that you weigh, how about 50 kilograms? You and the skateboard, okay? 2.2 pounds per kilogram, so that's somewhere around 110 pounds, something like that. We want to know how high you are off of the ground if you have 12,000 joules of energy. So we know you weigh 50 kilograms. We know you have 12,000 joules of potential energy. What's your height going to be? Okay, pretty easy. We're just going to plug and chug. Whenever you see energy and height, you're thinking potential energy. Your potential energy is 12,000. We already know your mass is 50. G is always the same. It's 9.81. And we're going to solve for height. So, pretty easy, right? We just got to get height by itself, so we'll divide by 50 and 9.81 on both sides. So we'll have 12,000 divided by 50 times 9.81, and our height will equal somewhere around 24.5 meters. Okay, so that's pretty high off of the ground, right? A meter's about 3 feet. Okay, so 60, so you got about 75 feet up in the air. Okay, that's pretty ridiculous. So that is potential energy, and that's about as complicated as it's going to be. Just make sure that if I give you something in grams, you're converting it to kilograms, and always make sure that your height is in meters. The next thing we're going to talk about is kinetic energy. Kinetic energy, similar to potential energy in that it's measured in joules, but its equation is 1/2 mv squared. So like I said, Ke stands for kinetic energy, and it is also measured in joules, okay? 1/2 is just 1/2. M, once again, is mass. And just like potential energy, it is also measured in kilograms. I know in chemistry we mainly deal with grams, but for energy problems like this, it's measured in kilograms. And then V is velocity. Right? I said this was the energy of motion. Well, that motion is just velocity, how fast you're going in a certain direction. And velocity is measured in meters per second. Acceleration is meters per second squared. Velocity is meters per second. So let's go ahead and let's do a couple equations or examples here where we're using that equation of kinetic energy equals 1/2 mv squared. So our first example here, it says, what is the energy of a 30 kilogram boulder rolling downhill at 10 meters per second? So it wants energy, and if I had height in here, you'd probably be thinking potential energy, but now I have velocity here. So now we're thinking kinetic energy. So we got to be thinking Ke equals 1/2 mv squared. So the only thing you really have to be wary of here is that when we plug in velocity, make sure that you square it first before anything else. So I'll show you what that means. So we want kinetic energy. We know mass is 30, and we know velocity is 10. So what a lot of you will do is you'll go 1/2 times 30 times 10, and you square all of it. Don't do that. square velocity first, right? PEMDAS, we do the exponent before a lot of other things, okay? It's parentheses, exponents, multiplication, division. Exponent comes first. So what I'll do is I'll take 10 squared, which will equal 100. Now I can multiply it by everything else in that problem, right? 1/2 times 30 is 15. 15 times 100 is 1,500 joules. Okay? So just make sure that you're doing your velocity squared first. That's the main thing. But other than that, it's just plugging and checking. Let's do one more example. My next problem, how fast is a 1 kilogram meteor traveling if it has 500,000 joules of energy? So you see this, you see it's got some energy, and it wants to deal with speed, right? It's asking how fast. So we know we're probably going to be using our kinetic energy equation, okay? So let's just start plugging in what we know. We know kinetic energy is 500,000. 1/2 is always in there. And my mass is 1 kilogram V squared, okay? So the best thing we can do right now is just get V squared by itself. So we got 500,000 here. Let's divide by 1/2 and 1, which again is just 1/2. 500,000 divided by 1/2 is just 1 million. So I have 1 million equals V squared, but I want to get V by itself, so then I square root both sides. And velocity, the square root of a million is just 10,000 meters per second. I don't know if that's, I guess that is possible. For a meteor, I don't know. The speed of light is 3 times 10 to the 8th meters per second. So yeah, I guess that's possible. Maybe in space, maybe it got blasted out of a supernova or something like that. Okay, so that is kinetic energy. Let's talk about energy a little bit more and how molecules react to those types of energies. So first thing we're going to talk about is the law of conservation of energy. That says law up there. If you get rid of the glare, law of conservation of energy. And it's just the same as the law of conservation of mass. It's just energy is not created or destroyed. It only changes forms. Right? So like, you're not 100% efficient. If you eat food, okay, you don't use all your energy wisely. Sometimes it gets just released as heat. If you're walking, sometimes it gets released as friction on the ground. When the universe was created, whichever way you believe, that's the same amount of energy that is here at the beginning of the universe as it is now. A lot of that energy is actually expanding out the universe, so it's getting bigger and bigger. So let's talk about some things that deal with energy, which are temperature and heat. Temperature is kind of how we measure heat. Temperature is the measure of motion in molecules, okay? So it's the measure of how fast molecules are moving. The faster the molecules are moving, the hotter the temperature. The lower the molecules are moving, the colder the temperature. So if we were looking at something like warm water, those molecules are going to be moving a lot faster. So let's say this is warm water. So those molecules are moving really quickly. They're bouncing all over one another. They're transferring energy. They're heating up the water. They're heating up the beaker. Whereas a cold beaker, those molecules are going to be barely moving. Okay, they're not going to be bumping into each other too much. The energy has left them, and they are moving really, really slow. So the temperature is higher in this warm beaker because the molecules are moving faster. The temperature is lower because the molecules are moving slower. And let's talk about heat. Temperature and heat are totally different. Temperature is just the measure of how molecules move, while heat is the flow of energy due to a temperature difference. Heat is the flow of energy due to a temperature difference. So I want you to start thinking of things not as cold, but things as just lacking heat. Okay? So things are no longer cold, things just lack heat. So heat transfers to things, and it speeds up those molecules. So when heat is going into something, those molecules speed up, the temperature goes up. When the heat leaves an object, those molecules slow down and the temperature goes down. It doesn't get colder, the heat just leaves. Okay, so we got to kind of talk about that flow of heat. If it's flowing into something or out of something, we have specific terms for that type of heat flow. Okay, and those are called exothermic or endothermic. Okay, exothermic or endothermic deals with the flow of heat. So again, we're just focused on heat. We're not thinking of cold. Nothing's cold. It either has heat or it loses heat. So, exothermic means heat is released or heat escapes. Okay? If you are a person and the heat leaves your body, you're going to get colder. Okay? The surroundings around you are going to get hotter, but you yourself are going to get colder. So when heat leaves, it exits, it is exothermic. So let's say I have a puddle of water here, right? And let's say that, there's my sweet arrow, the heat is leaving the water. Well, if the heat leaves the water, that water is going to get, not move around so much, those molecules are going to get closer together, not move so fast, and it's going to turn into ice. Obviously, it's not going to form a cube on its own. I'm just demonstrating that. When the heat leaves or exits, the water is going to leave, or the molecules are going to get closer together, move slower, and it's going to get turned into a solid. Again, we're not using the words cold. I'm trying to avoid that. Heat is leaving, exothermic. It's exiting. And then, of course, there's endothermic, where heat is going into, or heat is being absorbed is a better word to use, right? So if something is absorbing heat, if you're absorbing heat, you're getting warmer. You're getting sweaty maybe a little bit, okay, you're getting hot. So endothermic is heat is being absorbed. Heat is going into. Endo sounds a little bit like into. Heat's going into something. So now if we had a ice cube, and we decide to put heat into that ice cube, all right, heat's going to go in there. It's going to speed up those molecules. They're going to break their intermolecular forces a little bit, and it's going to turn into water. All right, it's going to turn into water. So let's go ahead and let's name a couple processes and see if they're exothermic or endothermic. So we have our examples here, and we're going to list them as exothermic heat leaving or endothermic heat going into. So I look at a candle flame, right? If I think about a candle flame and I put my hand next to it, heat is being released, right? Heat is getting released into my hand. So for the candle, it is a exothermic reaction. Heat is being released. Evaporating of water. Let's think about that. Evaporating water, right? I'm going from a liquid to a gas. So in order to go from a liquid to a gas, I got to heat up that water. I got to get those molecules moving a little bit quicker. So to do that, I got to put heat into the water to turn it into a gas. So that is endothermic. Cooking an egg, right? To cook an egg, I got to put heat into that egg, right? To cook it, right? You don't put it in the refrigerator and try to get heat out of it. You try to put heat into it to cook. So it is endothermic. The next one is the forming of snow, right? If we're forming snow, that's usually going from a liquid to snow, which is just like a tiny ice particle. So heat has to leave the liquid water for it to turn into a solid. So that's going to be exothermic. And then condensing of water. If you think about that, that's water vapor turning into a liquid. So that means that heat has to leave in order for those water molecules to get closer together and condense. So that is also exothermic. So be ready to explain if something is exothermic and endothermic. Remember, you're just focusing on where the heat is traveling. Is it going into an object or is it leaving an object? So the next thing we're going to talk about is thermodynamics. Thermodynamics is just a study of energy. So really when we're talking about thermodynamics for honors chemistry, we're just dealing with delta E equals Q plus W. Seems like a pretty simple equation. the thing that you really got to focus on is if heat is being released or absorbed. But let's talk about this. Remember, delta means change. So E stands for energy. So delta E just stands for change in energy. Q is just a fancy way of saying heat. And W stands for work. So the change in energy is just heat plus work. And in this equation, energy is going to be in kilojoules. So 1 kilojoule equals 1,000 joules. And what we really have to focus on again is if heat is being absorbed or is it being released. So for work, we can absorb energy by eating, or we can release energy by working, putting energy into an object. For heat, we can release heat or we can absorb heat. Well, what does that mean as far as these guys go? Well, if heat is being released, that means that the sign is negative. So if it's exothermic, the sign for Q or W will be negative. If heat is being absorbed, so endothermic, the sign is going to be positive. Okay? So keep that in mind when we're trying to determine signs of Q and W. If you release heat, Q is going to be negative. If you absorb heat, Q is going to be positive. If you do work on an object, you're releasing energy, work is going to be negative. If somebody does work on you, like is pushing you around, then you're absorbing energy and work is going to get positive. So let's do a couple examples where we have to look at the wording and determine if Q and W is positive or negative. So our first question says, calculate delta E when a gas absorbs 45 kilojoules of heat and does 29 kilojoules of work. So we want delta E, so we want Q and W. Well, Q is heat, right? And W is work, or 29 kilojoules. The thing is that we got to determine the sides of both of these guys. So if it's going to be negative or if it's going to be positive. So here it says the gas absorbs 45 kilojoules of heat. Remember, when we absorb heat, that's going to be positive. So our Q is positive 45 kilojoules. And you do 29 kilojoules of work. When you do work, you're releasing energy, right? If you push a wheelbarrow or a shopping cart, you're putting work into that. So you're releasing energy. So that's going to be negative 29 kilojoules, okay? If somebody's doing work on you, you're absorbing energy, but if you're doing work, you're releasing energy, right? So we absorbed heat, we released some work, we put those together, 45 plus a negative 29 will give us an energy change of, I think that's 16, correct? Yep, 16, that's going to be kilojoules. So overall, the change was 16 kilojoules, and that's positive. So this whole process ended up being endothermic. It absorbed more heat than it's released, so the surroundings probably got colder because heat was going into that gas. Okay, let's do another example. So our next example, it says a system releases 125 kilojoules of heat and 104 kilojoules is done on the system. Calculate delta E. So again, we're finding Q and W and just determining the sign. So we got 125 kilojoules of heat, so that's our Q, and it says it was released. So our Q is going to be negative. Heat's released, it's going to be negative. And then 104 kilojoules of heat or of energy is done on the system. So 104 kilojoules, let's say, of work is done on the system. So if you're doing work on something, you're putting energy into it. So if work is being done on the system, energy is put into the system. And remember, if heat is going into something or energy, it's going to be positive. So it'll be positive 104. Okay? If you're doing work, released. If work is being done on something, absorbed. So released, negative, absorbed, positive. We add these together, you should get negative, I can do math, 21 kilojoules. Okay? So overall in this total process, the energy change was negative 21 kilojoules. So this was exothermic. So the surroundings probably got hotter. A lot of energy was released. Let's go ahead and let's talk about that calorie and joules real quick. So that is it for energy change. Let's talk about the calorie and joule conversion. Like I said before, not an example, 1 calorie equals 4.184 joules. Okay, and a calorie is different. A calorie in food is actually 1,000 calories. So it's actually a kilocalorie. So if you have a soda that says it's 100 calories, usually that's with a capital C. All right, that's actually 100,000 calories. Okay, so on your food and everything's measured in kilocalories, but again, that's actually so again, if the soda says 100 calories, you're actually ingesting 100,000 calories. Okay, so what we're dealing with is the smaller version. We're dealing with just the most basic. Don't be confused by what's on your food labels. Just know that they're lying to you, and you're actually getting 1,000 more calories than you think. Okay, so in our situation, we're dealing with the small one. On food, it's all kilocalories. So I'm just going to have you convert things from calories to joules. So let's say that I have 300 calories, and I want you to go to joules. Okay, this 300 calories, okay, that's actually 0.3 calories on food labels. Okay, so let's go ahead and let's do this conversion. So we have 300 calories, and I know for every 1 calorie, it equals 4.184 joules. So all we do is we take 300 times 4.184, and that is going to be 1,255.2 joules. Okay, so that's just one conversion you'll have to do. Let's do an example where we're actually looking at a food label. Let's say that a food label, say piece of candy, it is 50 uppercase C calories on a food label. And I want you to convert to joules. Okay? Well, remember, the 50 calories on that candy is actually 50,000 calories. Okay? Because what they give you on your food is in kilocalories. So we actually don't have 50 calories if it's labeled on a food label. We have 50,000 calories. So what we'll do is we'll go ahead and do our conversion again. For every 1 calorie, 4.184 joules. And I got my handy dandy calculator here. Let's go 50,000 times 4.184, 209,200 joules. Okay, so that's all I'm going to be asking you as far as converting from calories to joules. So that is our intro lesson on thermochemistry. Make sure that you know about potential energy, kinetic energy. You know how to show the transfer of energy being exothermic or endothermic. You could calculate energy change by taking Q plus W and determining the proper sign. And that you're able to change calories to joules, and knowing that the calories listed on your food is in kilocalories and is actually 1 calorie on your food is worth 1,000 calories in science measurements. So that's it for today. Let me know if you have any questions. Have yourselves a good day.